Okay, hello and welcome back. So now let's move to the second case. Okay, again, another very simple case is the Laplacian operator, Poisson equation, Laplace equation. Okay, so let me present you this case. Okay, so what we're going to do is this case. Okay, so again, we have a square domain with these boundary conditions. Okay, here I call it the field, the field I call it T, but doesn't mean that it's temperature, it's just about a letter. So T0, 0, 0, these dimensions, initial conditions, okay, 0, and then here at the top, we have this non-uniform boundary condition. I will show you how to set up this one. So again, we're solving the general transport equation, but with this with these boundary conditions, the equations are going to reduce to this. Okay, so now see that we have no convection. Okay, so Laplace equation, Poisson equation, no source there as well. And we're going to solve this. So this is a smooth operator. So in the meshes, in the cases that you have, you're going to have different meshes, okay, like triangle, polyhedral. So play around with all the meshes and you can see the influence of the mesh element, okay, in the quality of the solution, but also in the discretization schemes, okay? So the analytical solution of this problem is this, okay? With the given boundary conditions, physical properties. So this is another very nice case validation case. So this is, we're going to work at it again, a steady case with under-relaxation, and then I'm going to move to a steady case to show you how to choose again the time step, okay? Again, remember, this is a problem that probably you are not working with this, you are not going to find it in reality, but these operators that you have here, you are going to find these operators in your equations. And in particular, this Laplacian operator, you find it in all equations, I have to say, momentum, energy, and all the turbulence models. You have the Laplacian operator, okay? That is a delicate operator. We're going to see why. Okay, so let's work it out, the case. So you have is you download your cases, see that you are going to have Fluent Laplace, and see here that you have different cases, okay? So you have a quad mesh quartz, quad mesh fine, triangular mesh quartz fine, then you have a 3D polyhedral mesh, triangular mesh. So feel free to play with the different geometries. I'm going to open here a 2D geometry, and I'm going to open the triangular mesh, okay? So see what I was mentioning in the previous tutorial, double precision. I don't see any reason why not to use double precision. In this previous case, I mentioned that you can rerun it without this one, you will see the influence. Here, I will enable, okay? And let's run. Okay, so let me go here. Let me put it here. It's a 2D case. Let me start it. Again, run without the one processor. These are very small cases. Okay, so there is no need to run in parallel. It's likely that it will slow down your computation. Okay, so not necessarily if you put more processors, it's going to run faster. Sometimes it's going to run slower. Okay, so we are here. Let me read the mesh and case. So I want the triangular mesh, the quartz one. Okay, so we're in here. So let's see again the case setup here is pretty standard, okay? How to set up these boundary conditions. Here I will show you how to set up this one. And again, we're solving the positive scalar. So we're going to enable this one, okay? Disable the flow equation. We didn't have flow here. And by setting velocity 0, this one goes away and you have this equation, okay? So again, you go here. First we go steady. Models, okay, everything disabled, doesn't matter what you put there, but what is important is here you need to go here, user defined scalar. So you add one equation, you have it there, and now we set up the properties for that scalar. You set up here, okay? So here is you go here, these properties doesn't matter, we're not going to use that. See that you define your coefficient, diffusion coefficient, which is 1, okay? So again, go here in the equation, this is 1. Okay, we have it there. There are no sources, so as you go here in the domain, okay, no sources, you want to enable sourcer of some other options, you have it there. So now you go into boundary conditions. Okay, so see that the naming that I gave is the top, bottom, left, right. Okay, so we check left, it is a wall, and the value there of the UDS is this one that we're solving. It's a specified value, the slash, so see that specify. All of them are the slash. If you are using Newman, will be the flux, specify flux. So 0, the same will be right and bottom. But for the top, to give non-uniform boundary condition is as easy as this. See here that you can put the function there. Okay, so see here that you have the option expressions. So in an expression, you can put any function. Okay, so all you have access to all the mathematical operators, everything. Okay, and also to all the functions fields that is safe by Fluent. So here I'm not going into details. You can go to the help manual, okay, and see how these expressions work. But see here that you have sign operator, this is the pi constant, and see this one represents the x coordinates. Okay, so as you go here, the analytical solution, you see pi's, and you have it there. Okay, so this is how you define here you have access to hyperbolic signs and everything. Okay, and this is important also. You need to give dimensions. Okay, you need to give the right dimensions, but this is relatively easy. Okay, so here you can put many things, and also here I think you go here also you have access to the expression library. Okay, so go to the help manual. I recommend you to visit that one. So this is your case definition. Now if we go methods here, this doesn't matter, nothing to do here. What is important here now, we're focusing this in the gradient operator and in this one. Okay, so if we go back to the equation, see that for us this is important, this gradient, we have that gradient there. Okay, so all these methods that you have here are high order methods, are very accurate method. Personal experience, I think this is the best one. Okay, so you can play with all these methods, but all of them are accurate. So Fluent is just giving you accurate options. Okay, instead here when you go to the user scholar, this one, okay, in this case we're not using that we don't need to use this one. Okay, in the equation that we're solving, that one will correspond to this one, so there is no problem, you can put anything there. Okay, so how this operator solver is using a method is the central difference. Okay, but it does corrections according to the mesh quality. So let me show you the mesh quality. The mesh. So this is the mesh that we have. Okay, so when I talk about when you compute that out, the Laplace operator between cell centers, you use central difference. But when you have non-uniform meshes like this, what you have is that you have also a cross derivative gradient. Okay, so you have another gradient, a secondary gradient in this phase. So you have a gradient normal to this phase, but also you have a gradient tangential to the phase. So let me go here back. Let me set here and draw that what's explained. So you have a gradient normal to the phase. Okay, but due to mesh quality, you have a gradient that is tangential to the phase. And it might happen that this gradient tangential to the phase, due to mesh quality, can be larger than this one. And this gradient that is much larger, it will add oscillations, numerical diffusion, and instability on your mesh. So this is why it's very important to have good quality meshes, to reduce the contribution of this secondary gradient. Okay, so Fluent already does a very good treatment for that, but also it gives you some options to correct that one. So as you look at here, let me close here, see that you have this option. It's basically to reduce that. Okay, and this is particularly important if you are doing heat transfer and stuff like that. Actually, you are solving this Laplace equation, but also it's important because you have this same operator in your turbulence equation and everything. But this is, I don't want to go into details. So this is what we're solving, and again, to control the evolution of this problem. Okay, because at the beginning we didn't have time derivative. This is the under-relaxation factors. Okay, so let me initialize this problem. Okay, so everything's 0. Okay, in this I put an animation here, and something that I want to mention, that this can slow down the computation. So as you go back to the previous tutorials, I had this enabled, but I was saving the files, and that was slowing down the computation. Here I'm putting everything in memory, so it will be faster, but can happen that you will fill your memory with these images. Okay, so be careful with those options. So we're done, and let me put here calculate and see what is happening is your solution is evolving. There is no time here. Remember, this is controlled by the under-relaxation factors. Okay, so see that your residuals see that are going down, and you reach here, okay, the maximum number of iterations, okay. But let me see here my residuals, okay. So in my residuals I have this, okay, I disable this option, let me enable, and you have convergence, okay. So now let's do some sampling. So I'm doing sampling in 3 lines. I created 3 lines, and let me go here. If I sample in this one, save plot, and there you have the solution, okay. So you have this, see that, a perfect agreement, and you can go to any line, okay. So those 3 lines, and let me open the 3 files and see that we have a perfect agreement in the 3 cases, okay. So again, we are controlling the evolution using the under-relaxation factor. So if I go back here and see that if I reduce this, and let me initialize again, okay, boom, boom, see that the evolution is much slower. In theory, it's much stable, but this will take a really long time, okay, to get the converged solution. So this is a compromise, as I mentioned, okay. So usually my advice 0.7, okay. For all variables, pressure usually is 0.3, okay. But in this case, again, we're not solving pressure. See here, equation flow is disabled. So let me increase it to 0.7, what we were doing previously, okay. Okay. And if I rerun, we have the evolution there. Now I enable also my residual, so I think it should stop very soon. And voila, there you have, okay. Now I didn't reach convergence. Here we have convergence, 113 iteration. And if I increase this to 1, I still know that this case will work, okay. Let me go here. See that in 4 iterations you have convergence, okay. So be careful, don't be fooled by the fact that you converge faster, okay, because getting solutions, if this is not about getting fast outcomes, it's about getting accurate and stable solutions. So 1, okay, in these simple cases is working, but it's better to use 0.7, 0.8, okay. And let me sample these 3 solutions, and let me see if we have good values. Good, this, and this. Okay, so we load 3, and yes, we have, yeah, a good agreement, very good agreement. Okay, but be careful, okay, that not necessarily now you're converging super fast. So in this case, probably 0.8 would be a better value, okay, a better compromise between accuracy and speed. So if I go here, so that is significantly slower, okay, but we know that is more rows, okay, 70 iterations. So now that I want to show you, by the way, you go here, and as you change this method, you will pretty much, I think we're going to have the same value, but in this case, the gradients, they're acting in this solution, okay. Remember that in your equation, you have this gradient here, okay. In numerics styles, you will have those gradients plus the pressure gradients or energy gradients, all the gradients that appear here. So see that a different method, okay, it's converging same way. So let's see, I'm quite sure that we're going to get the same results, not big difference. So let's see that we compare here with the analytical that we have. Okay, so see in this case, there is a difference, okay? So now probably, okay, so see that a different method to compute gradients is given here in these 2, okay, in 0.5 where you're sampling is given a different, okay. So this is interesting, okay. So see the green Gauss cell basis. So now let me change to the green Gauss no basis, that this tends to be more accurate method. Still, these methods are very accurate. So if I rerun this, initialize here, okay, and let's rerun and see what happens in this case. Okay, it's evolving, it seems that rich, and let's see the outcome here. Okay, so the 3 quantities there, and this, and this. Okay, again, we see that we have that different. And if we go to least square, okay, so pay attention that this is not this run the solution. This is something related maybe to accuracy. So I change to least square now. Okay. So 0.8, least square there, and let me run. So using the least square method, okay, 70 iterations. Well, probably I'm doing something wrong. So let's see what. You, and you. Yep. I don't recall. Oh, probably. Oh, yeah, yes. So the least square also, but it's accuracy problem. So let me reduce now the accuracy here. Okay. And see the importance of the accuracy. Even in this simple problem, the accuracy is important. So initialize and let me run. Okay. And let me increase this one to 1000. Okay. So now I reduce the tolerance, and let's see what happens. Okay, much better. So see that your tolerance going down. I should arrive 10 to the minus 4. Okay, so we have this, and if we go back here, and now we open you, and you. See that now we have a much better agreement, okay? So this one in the top, very good agreement, but then this one, it needed more time to evolve the solution, okay? So see the importance of the tolerance, okay? So even such a simple problem, you might be, you might get a little bit confused and you might start to try something else. So see that in this case also tolerance is a very important parameter to set up. Okay, so then you can play with different methods, but I'm quite sure that you're going to get the same outcome. I'm not going to do it. What I'm going to do now is let me enable now the same problem. Let me enable now the time derivative. Okay, so pretty much it's the same, but now I'm going to control my problem. This one is still you can use it. So this will give you extra stability. Same idea, do not put too large values, probably leave it in 0.8. But now you control everything using your time step. So let me use this time step, okay, a large time step. So let me put here 100 iterations, and let's see what happens with 100 iterations. Let me initialize here, okay. So let's see what happens with this time step. Okay, so we should get a good solution. So it's running, okay. So inaccurate, okay, So see that this indication, look at that, what is happening here, you have the residuals, but this is an indication, you see that they are not going up like in other cases that will be running in the tutorial of the cylinder, because when you have this one, this is a clear indication that this is an steady problem. And see that now here, it is starting to converge into iterations. Okay, so this is already telling me that this is a steady problem. So I see here that I have reached here that steady state. Okay, clearly you can see that it's iterating more. Okay, so you need to do sub iterations and everything. Okay, but now you have your time dimension. Okay, and if I open here, so that. You see that you have a very accurate solution. So in theory here, I can go back and choose very large, even larger time step, and it will converge the same, okay? This is a smooth operator. So it shouldn't give you problems converging. So now you choose that one. See that at the beginning, it takes longer, but then as it keeps advancing, it will reduce the number of iterations that it does. Probably, yeah, I chose a time set that is too large. But yeah, this one should be a solution. Okay, so if I go here, let me go back here. This is okay. Okay, so as here you see that doesn't matter your physics. Now you can go steady or unsteady, but be careful that steady hypothesis or assumption is very questionable, okay? And you have to be careful that you need to control the accuracy using under-relaxation, but also under-relaxation, you need also to modify residuals, like you have seen in this case, that it was sensitive to those residuals. So at this point, I'm done with this case. What I asked you now, I invite you to just run different geometries, and you will see the different meshes, and you will see different convergence rates. And it's likely when you run this polyhedral mesh, probably it's likely that you will realize that this polyhedral mesh is the one that is going to give you better results, okay? And it will convert faster. Okay, so that's all for this case. Thank you for your attention. See you in the next video. Bye.